Hello everybody, welcome into another lesson. So today we are going to start the unit on solving systems of equations. And today we are going to solve systems of equations in two variables using the substitution method. First we'll start out with some linear equations and then we'll get into some nonlinear ones. But the idea is when you solve a system of equations, you're trying to find where the two lines intersect, or if they intersect at all, or if they're the same line. And we'll go over some examples of that and what all that means. If it just has one solution, if it has infinite solutions, or no solutions. So there are two methods for solving systems of equations without involving matrices. Well, there's actually a third method. The third method is graphically. You could put these into a graphing calculator and see where they intersect. But what we're going to focus on are the other two methods. Today's version is going to be substitution. The next lesson will be elimination. That's the other method without using matrices. So when you do substitution, the idea is you're going to find the value of one variable in terms of the other and substitute it into the other equation. So you have x minus y equals 0, and then you have 5x minus 3y equals 10. Well, the first equation would be pretty easy to manipulate to simply make this y equals x. So we got y equals x, we derived that off the first equation, so we need to take this y equals x and put it into the second equation. So we'll end up having 5x minus 3, and then if y is x, this would be 5x minus 3x equals 10, which would give you that 2x equals 10, so x would equal 5. And then you can take this x equals 5, put it into your substitution equation, you'll literally get that y equals 5. So your answer is going to be an ordered pair. You'll end up having the ordered pair 5, 5 as your solution to this system of equations. So that means these two lines intersect at the point 5, 5. All right. So that was the first example. I got several more. And as I said, we'll start off linear, then we'll get harder. Alright, so we have x plus 2y equals 1. Then we have 5x minus 4y is going to be equal to negative 23. So we have x plus 2y equals 1 and 5x minus 4y equals 23. We want to use the method of substitution. So usually that's ideal if one of your variables has a coefficient of 1. If we look in the first equation, the x variable has a coefficient of 1, so we can get a substitution value for x in terms of y. So this x plus 2y equals 1 would turn into x equals 1 minus 2y. So we found the substitution for x. Now we derived it from the first equation, so we got to take that and stick it in the second equation. So this would be 5 times that value of x, which was 1 minus 2y. All that minus 4y equals negative 23. So you would end up getting 5 minus 10y minus 4y is equal to negative 23. So you would get 5 minus 14y equals negative 23. So you should end up getting that 14y equals 28, which would mean that y equals 2. Okay, we found the y value, so what about x? Well, just stick that y into your substitution. So you would get x equals 1 minus 2 times 2, which would equal 1 minus 4, or negative 3. So you got an x value of negative 3, a y value of 2, so you should get the ordered pair negative 3, 2 as the solution to this system of equations, which means these two lines intersect at the ordered pair negative 3, 2. Alright, so we have 2x minus y plus 2 equals 0. And then we have 4x plus y minus 5 equals 0. Again, today we're only using the method of substitution. This actually would be very good for elimination also. And I'm sure most of you recall the elimination method, since we've been doing it all the way since Algebra 1 and every course in between. But we're doing strictly substitution today. So this here, if you look at the first equation, we can easily make a substitution for y. This would turn into y equals 2x plus 2. So we found a substitution for y. Since it's derived from the first equation, we will take this and stick it in the second equation. So this would turn into 4x plus the quantity of 2x plus 2 minus 5 equals 0. So that means 6x plus 2 minus 5 equals 0. So 6x minus 3 equals 0. So you would get 6x equals 3, which means x would have to equal 1/2. So we got an x value of 1/2. Now let's find our y value. So y would equal 2 times that 1/2 plus 2. So that's going to equal 1 plus 2, which is 3. So y equals 3, x is 1/2. So the ordered pair that's the solution to this system, where the two lines intersect, is going to be at the point 1/2, 3. One more easy one, and then we're going to get into some decimals and fractions and stuff like that. Alright, so we have 6x minus 3y minus 4 equals 0. Then we have x plus 2y minus 4 is equal to 0. Again, we want to use the method of substitution. So 6x minus 3y minus 4 equals 0. X plus 2y minus 4 equals 0. If we look at the second equation, we have a coefficient of 1 on the x. So we probably want to make a substitution for x. Solve for x in terms of y. So this could turn into x equals 4 minus 2y. Now, since we got the substitution from the second equation, we will stick that into the first equation wherever we see x. So we'll take 6 times that 4 minus 2y minus 3y minus 4, set that equal to 0. So you should get 24 minus 12y minus 3y minus 4 is equal to 0. So this would turn into negative 15y plus 20 is equal to 0, which would give you 15y is equal to 20, which would give you y equals 4/3. All right, so we found y. What about x? So x would equal 4 minus 2 times 4/3, which would equal 4 minus 8/3, which would end up being 12/3 minus 8/3, which also means x is 4/3. So both x and y are 4/3, so the ordered pair that's your solution, where the two lines intersect, is going to be located at 4/3, 4/3. All right. So those were real basic linear equations. The next couple, we're going to do some decimal equations. All right, so we have 1.5x plus 0.8y is equal to 2.3. Then we have 0.3x minus 0.2y is going to be equal to 0.1. All right, so we have a system of equations where you have decimals everywhere. How the heck are we going to deal with this? First thing I would do, get rid of the decimals from each of the equations. So there's only one decimal place in each, so we need to multiply both of these equations by 10. That's going to turn into 15x plus 8y equals 23, and then 3x minus 2y is equal to 1. Well, again, this actually would be more ideal for elimination, but we're restricted to substitution only today. So I'm going to go with the second equation, solve for y in terms of x. So this would turn into 2y equals 3x minus 1, which means y would equal 3/2 x minus 1/2. So this kind of proves that substitution's not always the most ideal method, but that's okay. That's completely all right. I mean, sometimes that's just what you got to do. Now, since we derived our substitution from the second equation, we'll stick it in the revised first equation. So this would be 15 times x plus 8 times that 3/2 x minus 1/2 equals 23. So you would get 15x plus 12x minus 4 equals 23. Then you should just get 27x is equal to 27, which would give you that x equals 1. Now all we have to do is stick that x value into our substitution, and we should get a y value. So y would just equal 3/2 minus 1/2, which would just be 1. So the ordered pair that represents your solution to this system, where the two lines intersect, is going to be 1, 1. That was a bit more work, but it's still good to show what you're up against. Let's do another one with decimals. All right, so we have 0.5x plus 3.2y is going to be equal to 9.0. There's a reason for that 0.0. And then 0.2x minus 1.6y is going to be equal to negative 3.6. Well, again, you have two more equations in the system that both have decimals. Our first goal should be to get rid of the decimals. Let's do that. There's only one decimal place in each, so we just got to multiply by 10. You would get 5x plus 32y equals 90. And then you would get 2x minus 16y equals negative 36. Well, I'm going to personally recommend we go with the second equation and make a substitution for x, because the coefficient on x is only 2. So that's going to turn into 2x is equal to 16y minus 36, which means that x equals 8y minus 18. So now we found a substitution value for x that was derived from the second equation. Let's put it into the first. So you'll take 5 times that 8y minus 18 plus 32y, set that equal to 90. So we're going to solve for y first. So this would end up giving you 40y minus 90 plus 32y is equal to 90. So you should end up getting 72y equals 180. So for y, both of these should divide by 18. Actually, they'll both divide by 36. You would end up getting 5 halves. So y would equal 5 halves. Now let's go ahead and put that into our substitution equation. We can get the value for x. So x is going to equal 8 times that 5 halves minus 18, which would equal 20 minus 18, or simply 2. So the ordered pair that's going to be our solution is 2 5 halves. That's where these two lines would intersect, would be at the point 2 and 5 halves. Or 2, 2.5 if you want to use decimals. You get the idea. So there's some decimals. Guess what's coming next? You guessed it, fractions. We're going to deal with some fraction equations. So let's go ahead and address those. Alright, so I have 1/5 x plus 1/2 y is equal to 8 x plus y equals 20. Alright, so we have 1/5 x plus 1/2 y equals 8, x plus y equals 20. Well, much like decimals, if you have fractions, your first goal should be to get rid of the fractions. That way you don't have any fractions. So the second equation is just fine, but we need to multiply the first equation by the common denominator. Common denominator of 5 and 2 is 10. So multiply the entire first equation by 10. You should get 2x plus 5y equals 80. And then you'll still have x plus y equals 20. Now we have a form we can work with a lot better. So I think it's pretty easy to see what substitutions we could do. Pick x or y. I personally prefer to substitute for y whenever possible. So the second equation could turn into y equals 20 minus x. So since we derived from the second equation, let's put it into the first equation. So that's going to be 2x plus 5 times 20 minus x equals 80. So then we'll get 2x plus 100 minus 5x would equal 80. So that would give you negative 3x is equal to negative 20, which would give you that x equals 20/3. So that one's not quite as nice, but that is the x solution. Now, what about the y solution? So y would equal 20 minus that 20/3, which would equal 60/3 minus 20/3, which would equal 40/3. So the ordered pair that's going to be your solution to this system where the two lines intersect is 20/3 and 40/3. So 20/3 and 40/3 is the solution to this system of equations. I got one more fraction, then we're actually going to do some nonlinear ones. Alright, so we have 1/2 x plus 3/4 y equals 10. Then 3/4 x minus y is equal to 4. Alright, so we got fractions in both equations. So we have 1/2 x plus 3/4 y equals 10. Then we have 3/4 x minus y equals 4. Okay, so first thing you want to do for each of these, definitely get rid of your fractions, right? So first equation, you have denominators of 2 and 4, so your common denominator is going to be 4. So multiply the entire first equation by 4. You should get 2x plus 3y equals 40. The second equation, definitely a common denominator of 4. You would end up multiply by 4. You'll get 3x minus 4y equals 16. Now we got forms we can work with. And we're still restricted to substitution. So let's figure out a form that's going to work. Since we have a negative on the y, I hate to say it, we're probably going to do we're probably going to substitute for y. So this will turn into 4y equals 3x minus 16, which would mean that y itself equals 3/4 times x minus 4. Alright, now we got a substitution value for y. Let's go ahead, since we derived from the second equation, put that into the first. So this would be 2x plus 3 times that 3/4 x minus 4 equals 40. So this would become 2x plus 9/4 x minus 12 equals 40. Alright, so that'd be 8/4 plus 9/4, so that'd be 17/4 x equals 52. So x would be 52 times 4/17. Let's see if we can get an even number for this. I don't think so. So far I have 208/17. That one's not very nice. Yeah, and in fact, it's not going to factor any further. So x equals 208/17. Let's see now what we come up with for y. So y is going to equal 3/4 times 208/17 minus 4. So that's going to end up equaling, let's see, 52 times 3, that's 156/17 minus 4. Well, 4 in terms of 17 is going to be 68, so 156 minus 68. I get 88/17 for y. So this one was a bit messy, but your ordered pair that's the solution is going to be 208/17 and then 88/17 where the two lines intersect. So this particular system was not quite as nice, but it's the solution. Alright, so we've dealt with all linear up to now. Now we're going to move into some nonlinear systems where it relies heavily on substitution. So let's go into some nonlinear systems. Let's say I have 2x minus y equals 0, okay? Then I have x squared minus y is equal to -1. All right, well, definitely, so you have a linear and a quadratic. To be precise, you're trying to figure out where a line and a parabola intersect, if they do at all. This second equation is the equation of a parabola. So let's see if they intersect at all. Well, okay, we definitely need to make a substitution. I'm going to go based on the first equation, and we're going to say that y equals 2x. So y equals 2x. So since we based the substitution off the first equation, stick that into the second, you'll end up having x squared minus 2x equals -1, which would give you x squared minus 2x plus 1 equals 0. Well, we have a simple quadratic for x, so this would actually be, this turns into a perfect square binomial. This would be x minus 1 squared would equal 0, which would just give you x equals 1. Again, that is technically two solutions. It's just, it's twice. So that means it's only going to touch the parabola instead of crossing it. It'll touch at x equals 1. Had we had two solutions of x, you would also have two solutions of y. But let's substitute that x equals 1 into our substitution. Y would just equal 2. So the ordered pair where the parabola and the line touch would be at the ordered pair 1, 2. So you'll get 1, 2 for where the line and the parabola intersect. All right. A similar equation. So you'll have x plus y equals 4. Then you'll have x squared plus y is equal to 2. So you have a system where you have another line and another parabola. The goal is to figure out where they intersect, if they do at all. Well, we're stuck to substitution for now. So I would go based off the first equation. Let's substitute for y. So that means y would equal 4 minus x. Now we'll stick that 4 minus x into the second equation. This would turn into x squared plus that 4 minus x equals 2, which would simplify into x squared minus x plus 2 equals 0. All right, well, if we look at this here, it almost looks like you could factor it, but we can't. It's not going to factor. You're actually going to just have to use the quadratic formula. So x would equal the negative of b, so negative 1 is positive 1, plus and minus the square root of that b squared, so negative 1 squared, minus 4 times our a, which is 1, times our c, which is positive 2, all over 2 times a, so 2 times 1 is just 2. So that would equal 1 plus and minus the square root of 1 minus 8, all over 2, which is going to equal 1 plus and minus the square root of negative 7 over 2. Well, wait a minute. We have the square root of a negative number. When we're solving systems of equations, we don't care about complex solutions. We only care about the real solutions. So in this case, there are no real solutions. That means this line and the parabola do not intersect. They don't touch at all. That's what that means geometrically and graphically. There are no real solutions to this particular system. All right, we got more. So we have 3x minus 7y equals negative 6. Oh, that's going to be fun. Then we have x squared minus y squared is equal to 4. So it's 3x minus 7y equals negative 6. X squared minus y squared equals 4. So we have a line, and this time a hyperbola. We're trying to figure out where a line and a hyperbola intersect. So your best bet, again, use substitution. That's the best thing you can do, because one's completely linear, one's completely quadratic. So I'm actually thinking we should substitute for x for once. So let's go based off of the first equation. That could mean that 3x equals 7y minus 6, which means that x equals 7/3 y minus 2. Yeah, that's not going to be fun to substitute into the second equation, but we got to do it. So this is going to turn into 7/3 y minus 2 squared minus y squared is equal to 4. So this would be 49/9 y squared minus 28/3 y plus 4 minus y squared is equal to 4. That just got very messy very quickly. Well, alright, so 49/9 y squared minus y squared, that would just turn into 40/9 y squared minus 28/3 y equals 0. I'm going to personally suggest, for all of our sakes, that we try to get rid of the fractions. So multiply everything by 9, you should get 40y squared minus, okay, what's 28 times 3? That's going to be 56, 84. So minus 84y equals 0. Well, for sure, we can definitely factor out a y to start. This would be y times 40y minus 84 equals 0. But we can definitely factor out a common 4 from 40y minus 84, right? If we do that, you'll end up getting y times 10y minus 21 equals 0. Okay, now we got a form we can work with. So y would equal 0, and then 10y would equal 21, which would mean that y equals 21/10. All right, well, we have two solutions for y, which means we should actually end up with two solutions for x. So we're going to have two ordered pairs that actually work for this system. So for y equals 0, we'll solve that first. That just means x would equal -2. So you should get the ordered pair -2, 0 as one of your ordered pairs. That would definitely work. Now the fun one's going to be when y equals 21/10. So x would equal 7/3 times that 21/10 minus 2, which would end up equaling 49/10. That minus 2 would really be minus 20/10, which should give you 29/10. So the second ordered pair you should get is 29/10, 21/10. So you have two ordered pairs that are the solution to the system of equations. You have -2, 0 and 29/10, 21/10. That's where the 2 points this line intersects this hyperbola. All right. Another very common set of problems is where a line intersects a circle. And it happens more often than not that there's no solution. Now, sometimes you will get solutions, but that's not an all-the-time thing. So let's talk about, for the next few, a line and a circle, if they intersect at all. So let's say you have something like x squared plus y squared is equal to 25. Clearly a circle, right? And then you have 2x plus y is equal to 10, which is a line. So we're trying to figure out if this circle and this line intersect. Definitely going to have to use substitution. Easier to substitute for y. So that means that y is going to equal 10 minus 2x. Now we can go ahead, substitute that into the first equation. So you'll end up getting x squared plus the quantity of 10 minus 2x squared equal to 25. So that means you'll have x squared plus 100 minus 40x plus 4x squared is equal to 25, which would simplify into 5x squared minus 40x plus 75 equals 0. Well, we can definitely divide by a common factor of 5. This would turn into x squared minus 8x plus 15 equals 0. This will actually factor very nicely into x minus 3 quantity times x minus 5 quantity equals 0. So that means you get x equals 3 and x equals 5. Since you have two x values, you're going to also have two y values. So that means this line is going to intersect the circle in two different places. So for x equals 3, y would equal 10 minus 2 times 3, which would equal 10 minus 6, or simply 4. So one ordered pair you're going to get is 3, 4. Now, we also have to consider for x equals 5. So y is going to equal 10 minus 2 times 5, which would be 10 minus 10, which is 0. So the second ordered pair you should come up with is going to be 5, 0. So the circle and the line intersect at 2 points, at 3, 4, and at 5, 0. All right, let's see. We have x squared plus y squared equals 1. We have x plus y equals 4. So again, we're going to figure out where another circle and another line intersect if they do at all. I'm going to say we pick the second equation and substitute for y. So that can be done as y equals 4 minus x. So put that into your first equation. You'll have x squared plus the quantity of 4 minus x squared, which would equal 1. So that would give you x squared plus 16 minus 8x plus x squared equals 1. So that's going to end up giving you 2x squared minus 8x plus 15 is equal to 0. And sadly, these don't really factor. So what we're going to have to do is we're going to have to use the quadratic formula. So x would equal negative 8, that's positive 8, plus or minus the square root of negative 8 squared, that's positive 64, minus 4 times 2 times 15, all over 2 times 2, which would be 4. So you would end up having 8 plus and minus the square root of 64 minus 120 all over 4, which should give you 8 plus and minus the square root of negative 56 all over 4. Well, you have a square root of a negative number, which means there's no real solutions. So we have no real solution to this system. What does that mean geometrically? That means the circle and the line don't even touch. There's no point of intersection at all. They don't even touch. So there's no real solution to that one. All right, so let's see here. Those are some circle examples. Let's do a linear and a radical. So we have y equals 2x plus 1. Then we have y equals the square root of x plus 2. Alright, so y equals 2x plus 1, y equals the square root of x plus 2. Well, look at your second equation. Before we do any substitution or anything like that, we have to go by the original equations. What is true for where a radical is defined? When the value under the radical is greater than or equal to 0. So we have to consider where x is plus 2 is greater than or equal to 0. Because if it's less than 0, you have an imaginary number, right? So that means that x must be greater than or equal to -2. If we get any value less than -2, we have to discard that value. It's an extraneous solution. So you can have that sometimes. But since these both equal y, you can set one equation equal to the other. So you can set 2x plus 1 equal to the square root of x plus 2. Now you just square both sides, you can get rid of the radical. This would turn into 4x squared plus 4x plus 1 equals x plus 2, which would turn into 4x squared plus 3x minus 1 equals 0. And I'm pretty sure this is actually going to factor. I'm pretty sure it will. 4x squared minus x plus 4x, so yeah, plus 3x minus 1. Perfect. So this factors nicely into a quadratic equation for x, where you get x plus 1 times 4x minus 1. Well, that would give you x equals -1, and then 4x equals 1, which means x equals 1/4. If you look at both of your solutions, they're both within the restricted domain of greater than or equal to -2. So both of these solutions are actually going to check out, which means we're going to have two y values. So pick an equation and stick it in. It doesn't matter which one you pick, you should get the same result for y. Personally, I prefer the non-radical. So for x equals -1, you would get y equals 2 times -1 plus 1, which would be -2 plus 1, which is simply -1. So you should get an ordered pair of -1, -1 as one of your ordered pairs. You have another one where you got to consider x equals 1/4. So y is going to equal 2 times 1/4 plus 1, which would equal 1/2 plus 1, which is 3/2. So the other ordered pair you should get is 1/4, 3/2. So the radical curve and the line both intersect at 2 points, at -1, -1, and 1/4, 3/2. Let's do another one similar to this. All right, so y equals 2x minus 1, and y equals the square root of x plus 1. So a little bit different, but similar. Again, we have to go, since we have a radical, we have to go by the original equation. So that means x plus 1 needs to be greater than or equal to 0. So this will be when x plus 1 is greater than or equal to 0, so x has to be greater than or equal to -1. If we get a solution less than -1, we have to discard it. Now, since y equals both of these, we can just set one equation equal to the other. So 2x minus 1 equals the square root of x plus 1. Square both sides to get rid of the radical, you would get 4x squared minus 4x plus 1 is going to be equal to x plus 1. Well, this would end up turning into 4x squared minus 5x equals 0. Well, let's factor this. So you'll end up getting x times 4x minus 5 equals 0. So you should again have two solutions. X would equal 0. and then 4x minus 5, no, 4x equals 5, so x would equal 5/4. Well, both of these solutions are within your domain of greater than or equal to -1, so we should, since we have two x solutions, we should have two y solutions. So pick an equation, stick these into. Let's go for x equals 0. So y would equal 2 times 0 minus 1, which would equal 0 minus 1, or -1. So the first point you should get is 0, -1, the first ordered pair. We also have to consider when x equals 5/4. Now, let's see. So that's going to be y equals 2 times 5/4 minus 1, which would be 5/2 minus 1, which would be a y value of 3/2. So the second ordered pair you should get would be 5/4 and 3/2. So the line and the radical curve intersect at 2 points, at 0, -1, and 5/4, 3/2. Now, let me throw a couple at you here that are going to be interesting. What if you had something like y minus e to the -x equals 1, and then y minus the natural log of x equals 3. Very interesting, huh? Take your pick and do a substitution. Personally, I like the looks of the second one better for a substitution for y. We could say that y equals 3 plus the natural log of x. So now we can substitute all that in. We should end up getting 3 plus the natural log of x minus e to the -x equals 1. Well, you have two inverse operations in the same equation. How in the heck are you going to solve that algebraically? As it turns out, you don't. Now, graphically, you might be able to. This is a fine example of a graphic solution. That's where you would have to put each of these into your calculator and graph them, and then use the intersect feature to figure out if these intersect at all, and you would probably get decimal approximations. So, and let's see here. What about 2 times the natural log of x plus y is equal to 4. And then you have e to the x minus y equals 0. Well, I think it's obvious we can use the second equation and set y equal to e to the x. So then you have 2 times the natural log of x plus e to the x would equal 4. Again, you have two inverse operations in the same equation. The only way you're going to be able to solve this system is graphically. That's your best bet. So sometimes it isn't simple algebraically. Sometimes you need to use graphing calculators and computers to solve it. I got 4 more exercises, then we're done. So, got a cubic one here with a quadratic. So y equals x to the third minus 2x squared plus 1. Don't need that big of a y. And then y equals 1 minus x squared. So we actually have a cubic equation and a quadratic equation. We need to figure out where these intersect. A cubic curve and a parabola, where do they intersect? Well, since y equals y, we can just set one equation equal to the other. So this would end up being x to the third minus 2x squared plus 1 equals 1 minus x squared, which should turn into x to the third minus x squared is equal to 0, which should factor nicely into x squared times x minus 1 is equal to 0. So you should get two solutions, x equals 0 and then x equals 1. So since you have two solutions for x, you're also going to have two solutions for y. So let's go for when x equals 0. Pick an equation, stick that 0 in. I like the looks of the second equation better. So y would equal 1. Well, 0 squared is just 0, so 1 minus 0 is 1. So one ordered pair you should get is 0, 1 for a point of intersection, but we also had x equals 1. So for x equals 1, you get y equals 1 minus that 1 squared, which would be 1 minus 1, or simply 0. So your second ordered pair you should get is 1, 0. So these two curves intersect at 2 points at 0, 1 and 1, 0. 3 more problems, then we're done. All right, so a similar type of problem, y is going to equal x to the third minus 2x squared plus x minus 1, and then y is also going to equal negative x squared plus 3x minus 1. So we have a cubic curve and a parabola. We need to see if they intersect at all, and if so, at how many points and where. So again, the domain for both of these is the set of all real numbers. There's nowhere it's going to become discontinuous. So let's set one equal to the other. So you'll end up getting x to the third minus 2x squared plus x minus 1 equals negative x squared plus 3x minus 1. So this would become x to the third minus x squared minus 2x equals 0. Let me just make sure I added right. Yeah, and yeah, okay. Well, we could definitely factor out a common x from this. You'll end up with x times x squared minus x minus 2. Now the big question is, can we factor this quadratic factor further? I actually believe we can. If we get x times, let's see, that'd be x and 1, x and 2. So let's see, that would be minus 2x plus x, or x squared minus 2x plus x, that'd be negative x minus 2. Perfect. So we have actually 3 factors of x. That means we're going to have 3 values of x. So x would equal 0, x would equal negative 1, and x would equal positive 2. That means these curves intersect in 3 places. So we should get 3 solutions for y. So for x equals 0, now just pick one of your equations. I like the second equation better. You should literally get y equals negative 1. So the first point you should get, the first ordered pair would be 0, negative 1. These do intersect at 0, negative 1. Now what about when x equals negative 1? So 4x equals negative 1, so y is going to equal negative of negative 1 squared plus 3 times negative 1 minus 1, Well, that would equal negative 1 minus 3 minus 1, which would be negative 5. So the second ordered pair should be at negative 1, negative 5. And then we have a third value of x. So for x equals 2, you're going to get y equals the negative of 2 squared plus 3 times 2 minus 1, which would equal negative 4 plus 6 minus 1, which would end up being 1. So you should also get the ordered pair 2, 1. So the three ordered pairs you should get as the solutions to this system are 0, negative 1, negative 1, negative 5, and then 2, 1. Well, that was a fun one. I got two last problems, and this is going to be a linear with a rational function for both of them. We need a linear with a rational. That's what we're going to do. So let's say you have xy minus 1 equals 0. And then you have 2x minus 4y plus 7 equals 0. So you have a rational curve and then you have a line. You need to see if and where they intersect. The problem is, in the first equation, it's x times y. So you're going to have an ugly rational expression if you try to do a substitution based off the first one. You're actually better off to do it off the second one. And I'm going to vote for once we make a substitution with x. So let's go based on the second equation. This would turn into 2x equals 4y minus 7, which would have to mean that x equals 2y minus 7 halves. Okay. Now go ahead and stick this substitution into your first equation. So that y would literally be based like y times x, so you could take y times 2y minus 7 halves, all that minus 1 equals 0. So you would end up getting 2y squared minus 7 halves y minus 1 equals 0. Well, let's get rid of that fraction. We should do that. Multiply the whole thing by 2. You should get 4y squared minus 7y minus 2 equals 0. I'm actually pretty sure these are going to factor. So you'll have a y, a 4y, that should be 2, and that should be 1. All right, let's figure out what equals what. 4y squared plus y minus 8y gives you negative 7y minus 2. Perfect. So this factors into the quantity of y minus 2 times 4y plus 1. So we should have two factors of y. So y would equal 2, 4y would equal negative 1, which means y would equal negative 1/4. So since we have two values of y, we should also have two values of x. So let's go ahead and stick these in for y and solve for x. So for y equals 2, that's going to be x equals 2 times 2 minus 7 halves. So that would end up being 4 minus 7 halves, which should end up being 1/2. So the first ordered pair you should get is 1/2, 2. So you should end up getting the ordered pair 1/2, 2 for your first coordinate. And then let's deal with for y equals negative 1/4. All right, so x is going to equal 2 times negative 1/4 minus 2, which would be negative 1/2 minus 2. which should end up being, let's see here. Where did yeah, I did, okay. It's minus 7/2. Where the heck am I getting 2 from? Excuse me. I knew something wasn't right. Oh boy, alright. So negative 1/2 minus 7/2, that's negative 8/2, which is negative 4. So the second ordered pair you should get would be negative 4, negative 1/4. So these curves intersect at 2 points, at 1/2, 2, and negative 4, negative 1/4. And I got one more problem like this, then we're done with the lesson. All right. Similar problem. We have another rational equation. This time xy minus 2 equals 0. And then 3x minus 2y plus 4 equals 0. So we have another rational equation and a linear. So we need to see where a rational curve and a line intersect, if they do at all. So again, substitution is your best bet since the first equation is x times y. I think it's going to be best we go based on a substitution for y in this case. The second equation could be rewritten as 2y equals 3x plus 4, which would then mean that y equals 3/2 x plus 2. All right, so we got our substitution. Now let's stick that into the first equation. So that would be x times your value of y, so x times 3/2 x plus 2, all that minus 2 equals 0. So this would be 3/2 x squared plus 2x minus 2 equals 0. Definitely, I'm going to highly suggest we get rid of the fraction. So multiply everything through by 2. You should get 3x squared plus 4x minus 4 equals 0. I want to see if it factors. I'm curious. I think it actually does. Oh yes, it does. Let's see. So we should have an x and a 2 and a 3x and a 2. Now which one's plus, which one's minus? 3x squared minus 2x plus 6x would be plus 4x, then minus 4. So this is going to factor into x plus 2 times the quantity of 3x minus 2. So now we can solve for both solutions for x. X would equal negative 2. 3x equals 2, which means x would also equal 2/3. Since we have two values of x, we're also going to have two values of y. So let's look first when x equals negative 2. So for x equals negative 2, y is going to equal 3/2 times negative 2 plus 2, which would just be negative 3 plus 2, which is negative 1. So your first ordered pair you should get is negative 2, negative 1. That's the first ordered pair you should get. Now let's look at when x equals 2/3. So y would end up equaling 3/2 times 2/3 plus 2. This literally just turns into 1 plus 2, which would equal 3. So the second ordered pair you should get would be 2/3, 3. So these two curves intersect at the points negative 2, negative 1, and positive 2/3, 3. Alright, so that's it for this lesson. Next lesson we'll go into the elimination method for solving a system of two equations. So I hope everyone has a great day. Take care.